But not all genetic variability has the same effect on the response to selection that we're looking for, that shift in average values from one generation to the next. So as you'll recall from your genetics class, we have some cases in which different alleles have a dominance and recessive relationship. So we call this dominance genetic variation. And in this case, because the homozygote and the heterozygote have the same identical phenotype, going out and measuring the phenotypes in the population and the variance in the phenotypes is not going to give you an accurate measure of the variance in the genotype, right? Because all of the individuals with the dominant phenotype are a combination of homozygotes and heterozygotes. You have no idea how many of which you have. So it's not giving you a good understanding of the amount of genetic variance there is in that population. We also have something called additive genetic variation. In your genetics class, you probably learned this as incomplete dominance. So in incomplete dominance, remember that the heterozygote has an intermediate phenotype between the two homozygotes. So that means that there's this one-to-one correlation between genotype and phenotype. Each genotype has its own distinct phenotype. So you can go and measure the phenotypes in the population and have that give you a good estimate of the actual genetic variability in that population. To get a good idea of how closely offspring will resemble parents, that relationship between phenotypic variation and genetic variation, we use only additive genetic variation. To look at this a little bit differently, let's imagine a situation where there's a gene with two alleles, A1 and A2. And in this first case, we're going to say no dominance. Okay, so this is what we called before an incomplete dominance situation. And we're going to assign phenotype values to each of these genotypes. So the A2 homozygote, we're going to say has a phenotype value of 2. We can think of this as A1 being a loss of function allele that doesn't produce a functional protein. A2 is a functional protein. You've got 2 copies of it. You get twice the protein product. In the case of the heterozygote, you get sort of a half dose of the protein product, and we're going to give it a phenotype value of 1.5. And let's say in the homozygote loss of function, we have a phenotype value of 1. That's what you get without any of this A2 protein product. So if we look at these phenotype values on a histogram showing the fraction of the population with each of these phenotypes, if you'll remember back to your Punnett squares, if you have 2 alleles of a gene, about half of the population will be heterozygotes, about a quarter each of each homozygote, and this is what your population is going to look like. So now, if we plot genotype in terms of the number of A2 alleles, so these ones have 2 copies of A2, this one has 1 copy, this one has 0 copies, this phenotype correlates. This is the phenotype value on the y-axis. The phenotype correlates very nicely with the genotype. We can plot a line through those points, and each point falls exactly on the line. We've got a very strong correlation between genotype and phenotype, so that means that there's going to be a very strong tendency for offspring to resemble their parents because each genotype has its distinct phenotype. Another way of thinking about that is that the variation in genotype is exactly reflected in the variation in phenotype. There's a one-to-one correlation. On the other hand, if you've got complete dominance, now our phenotype values are 2 for the A2 homozygote, also 2 for the heterozygote, because remember, complete dominance means that the phenotype of the heterozygote is identical to the phenotype of the homozygote. And then again, we've got a phenotype value of 1 for the A1 homozygotes. In this case, if we look at the fraction of the population with each phenotype, we've got 75% with 2, because that's a combination of both the heterozygotes and the A2 homozygotes, and then again 25% of the A1 homozygotes with a phenotype value of 1. So now if we plot these genotypes in terms of the number of A2 alleles against phenotype value, we do not have a nice straight line that we can put between these that all the points are going to fall upon. There's not this one-to-one correlation between genotype and phenotype that's going to make this a very predictable tendency for offspring to resemble parents. So this gives us another way to define heritability. So remember, what we want to get at is that portion of heritability that is going to be important to this response to natural selection, that shift in phenotype value from one generation to the next. So now, because we know that there's this direct correlation only when you use additive genetic variation, what we want to know is the proportion of phenotypic variation that's explained just by the additive genetic variation. This is the part that causes offspring to resemble parents. So we're going to give this a new variable, and for historical reasons, this variable is called h squared. Please note that there's nothing that's actually squared here. There's no taking the square root of this and getting h. The number that you get for narrow sense heritability, the variable that you use for that is h squared. So h squared now is going to be, again, the proportion of the total phenotypic variability that can be accounted for by additive genetic variance. So additive genetic variance divided by total phenotypic variance. Again, we're going to split out phenotypic variance into genetic and environmental, and then we've also split out genetic into additive plus dominance genetic variance. So this additive plus dominance genetic variance together makes the V sub g that we saw in the broad sense heritability equation, and then V sub g plus VE is going to equal the total phenotypic variance. So again, this is sort of a conceptual construction to help us define our variables. These things are not things that we can just go out and measure directly. Additive genetic variance, dominance genetic variance, and environmental variance. But we do have a way of actually measuring this. Because this is the variance that causes offspring to resemble parents, we can measure this just by comparing offspring and parents. We make a plot like this comparing parent values to offspring values. So let's go through this graph point by point here. So each point on the graph represents the average value for the two parents, mother's value plus father's value divided by 2, plotted on the x-axis, and then the mean trait value for all of the offspring of those two parents on the y-axis. Okay, so this point is one set of parents and all their offspring represented. So what we would expect is that for parents with really bad stinky dog breath to give rise to offspring with really bad stinky dog breath, and parents with nice minty fresh breath to give rise to offspring who also have nice minty fresh breath down here. To get a measure of the narrow sense heritability, we basically just do a linear regression, get a best fit line through this cloud of points, and the slope of that line is equal to the narrow sense heritability. So narrow sense heritability, h squared, can vary between 0 and 1 and take any value in between. So this tells us something about the relative effects of genes and environment on producing phenotypic variability. So in this case, if we take that slope, it's approximately 0.5. So let's look at what each of these ranges of value mean in terms of how we can interpret these graphs. Let's start here at the bottom with a heritability of 1. So again, as I said before, this is, in this case, the axes are tall versus short, again, but this is mid-parent versus mid-offspring. Tall parents give rise to tall offspring. Short parents give rise to short offspring. There's a very reliable correlation. So what this means is that most of the phenotypic variation in height in this population is due to genetic variance. This is exactly the same set of points that we looked at over here. This is a heritability of about 0.5. There's some tendency for tall parents to give rise to tall offspring and short parents to give rise to short offspring, but there's quite a bit of scatter around this, and the slope that you get with the best fit line is about sort of halfway in between. There's sort of equal contributions of genetic variance and environmental variance that contribute to the phenotypic variance in that trait. In this top case, when we do our best fit line, we get a slope of 0. So that means there's no tendency whatsoever for offspring to resemble their parents. And we can see this clearly by showing that The very shortest parents give rise to kind of average height offspring. The very tallest parents give rise to kind of average height offspring. The tallest offspring came from average height parents. The shortest offspring came from average height parents. It really doesn't matter how tall your parents were in determining how tall you were going to be. So this measure of narrow sense heritability, this tendency for offspring to resemble their parents, gives you this very, very important piece of Darwin's postulates that give rise to natural selection. How much of this variability in the population is actually going to result in a shift in trait values in the next generation? In other words, evolution by natural selection.